Hi everyone, welcome to Practical Software. Previously, we've seen the working principle of a LiDAR sensor and how to create the proper software interface to interact with this kind of sensor, leveraging abstraction, testability, position of the driver, and more. If you don't know what a LiDAR is, it is basically a sensor like this, which is capable of telling the distance between itself and some object that collides with the laser. Now, in the video, I've briefly mentioned very interesting applications you could use a LiDAR for. There is one that for some reason has always caught my deepest interest, which is scanning and mapping. Scanning and mapping algorithms are the core building blocks of what makes autonomous things being aware of their surroundings. Autonomous things like autonomous robots, autonomous cars, autonomous drones, everything that you want to be aware of the surroundings spatially, you probably want to do some scanning and mapping. I don't know why, but there is something about being able to computationally tell where you are, what is the location in the space that just makes me happy. Anyway, today I'd love to show you a fundamental step in the process of self-localizing algorithms that use point cloud data to build high precision maps, a process called point set registration. Point set registration, point cloud registration, also known as scan matching, is the process of computing the spatial transformation that leads you from a certain source point clouds to a target point cloud so that they perfectly match. Shall we break down what this actually means? The example that I'm going to show you is based on scanning and matching LiDAR scans. The actual point set registration can be used for other purposes, but to really show you the practical application that comes together with point set registration, the use case is exactly based on that. Imagine I'm in a room like this and I go to position A first. From that position, I look to my front, which is described by the y-axis, and I perform a two-dimensional LiDAR scan with my 360-degree LiDAR sensor. The point cloud that I'm going to produce is going to look like the one in the bottom left. And of course, we imagine points instead of the lines, because the actual data that you're going to get are points, not lines. But for the sake of facilitating representation, I've drawn lines instead. Now, I move from point A to point B and I perform a second LiDAR sweep. But that motion from point A to point B are both a translation and a rotation. So not only I translate myself, I also do a small rotation together. Notice that from that perspective, I am looking towards the first edge number one. This one, which is also this one. This is my new direction. And from that perspective, from that frame of reference, the point cloud that I'm going to produce is going to be a little bit different. The process of scan matching is basically taking a source point cloud and iteratively processing that such that you perfectly align that point cloud with your target point cloud. Something like this. Very naturally, you get exactly as an output of that algorithm the transformation T that led you from point A to point B. And by T in the two-dimensional domain is typically represented by X, Y, and theta. So Cartesian X, Cartesian Y, and the theta represent your rotation. Simple as that. There is one assumption, important assumption, that this transformation T is a rigid transformation. This means that the point clouds are assumed never be distorted like this. There is no scale factor, there is no distortion. They are as is, as they were captured by the sensor. There's no distortions whatsoever. To be fully able to do that process, there is a very important step that you have to be sure that is well done. That step is called data association or data correspondence. Data correspondence means that you have to somehow find the correspondent point of a source point cloud in the target point cloud. So this point matches this one, this point matches this one, this point matches this one, and this one matches this one. If you don't know anything about your data association, you are allowed to perform assumptions or approximations. For example, let's say I don't know any association whatsoever. I can start by taking the closest point from that one to this one, that one for this one, that one for this one. So I am allowed to perform these naive associations so that I can at least iterate and I can move my source point cloud towards the target point cloud. Data association allows you to establish connections between the source and the target, and it allows you to formulate the problem mathematically. This means that once you have your established source and target, you can create an error function, which is step number 2, that will be something that you want to minimize. And for your information, the process that I just showed you, which is assume the closest point for one in the target point cloud, the closest point to the other closest point in the other cloud. So if you iteratively do that, we are actually doing one of the classic registration algorithms called iterative closest point, ICP. To summarize, a very classic way to approach this problem is, first, you find your data associations. So for each point in the source, you try to find its corresponding to the target. Somehow you're allowed to do some heuristics. Second step is you define an error function. This error function will establish an error or distance between the correspondences that you found in the previous step. So this is typically a function of your source and your target, and you typically want that function to be minimized. And I'm going to kind of try to show you what this means. And the third and final step is to iterate over that many steps. So you first data association, define error function, build your problem, iterate it again. Essentially, doing those steps, you are moving your source point cloud towards the target point cloud. Perhaps you already understand how you can localize yourself with this. Imagine you have a baseline point cloud, a single target, or a map, like this one, and you move to different positions, and then you perform a scan, and then you try to match that, then you scan towards the target scan, the original scan, and then you move again and you try to match again, and then you move again and try to match again. Effectively, what you're trying to do is just trying to localize yourself in the space. If you have a map, a baseline, a reference map, and all the following scans are attempted to be matched towards this first one, effectively you're trying to localize yourself because you're getting all the different transformations over time. If you're thinking, okay, how would the program that does this would look like? Let me show you. This simple program that I built takes 2 or more point clouds as an input. It also takes a special address to which I can publish and render my data, my outputs, my results, so that I can just easily visualize the results. And you can give it as many point clouds as you want. The way it works is the first point cloud will be taken as the target, and every point cloud that comes after that, the first one, will be the new sources. So target is the static one, and every new one are sources point clouds. For that experiment, I have scanned the room of my studio from different perspectives with the LiDAR, the same LiDAR that I used in the previous video about LiDARs. By the way, this server that we published the data to is a gRPC server, something I already talked about in the channel. The way it works is we define a protofile like this. This protofile defines the interface and the data that my said server is expecting to receive. And the way it works is, for the particular purpose of streaming point clouds, I use a concept in gRPC called a stream. The client keeps pushing data over a channel, over a stream, and the listener just keeps listening for extra data as they come. It's not like the previous time I showed you this concept, which is just a one-time call. It is a streaming call, so I can open a channel and I can keep streaming my data and keep the connection alive. And that makes point cloud streaming quite efficient. Some of you might be familiar with something called ROS. And what I'm doing here is very similar to ROS. A video on that will come. And of course, the data types are also defined by this file. So here is the concept or a message or a point cloud is a repeated or a dynamic array of points, and each point is X, Y, and Z, and they optionally have color. So that's a very cool thing. It was an experiment that I did a while ago to demonstrate the capability of gRPC, and it ended up being this useful tool to render my point clouds. Back to the main program. This is just a loop iterating over as many scans as we give as an input to the command line. And here you see that the very first scan I added to an object called map. This map is a data structure that allows me to query whether points are close to each other. So this is actually a data structure that will hold the information of my points, where they are in the space. And this KD3 is a special data structure that allows you to query what are, in a very efficient way, what are the closest points of a certain point cloud to a given point query. So if you have a query like this, and you ask what are the two closest points, the KD3 will return to you this and this, if you query like here. Of course, you could have done it in a brute force. You could literally, for every point that you have in the source, you can query in every point that you have in the target, what is the closest one, which is the brute force. That's also possible. But yeah, for efficiency purposes, and because I already knew this data structure, I'm using that to be an efficient way to query if the points are correspondent, so that I can build that error function that I've talked about. Here I create a registration object. This is something I did in the library of this repository. This repository is my personal project on how to tackle this kind of problems. And here there is an object that allows you to abstractly establish and define a problem. Here you can indicate how many iterations you want to go as a limit. And here you can also indicate how far the correspondences should be. That's an important heuristic because you don't want to have, for every point in the source, to have a correspondence in the target. Imagine this being correspondent to this point just because it's the closest point. Sometimes it doesn't make sense to establish these correspondences. So we apply some kind of heuristic, some kind of filtering. And for example, if the point is too far away, they are not counted as correspondences or associated points. So it's generally a good practice to create this threshold. Here is just my publisher object. This is taking an argument as an address as an argument that will tell it's basically the IP address to which I'm going to push the data. And here I'm going to push pose as well. It's just the dot that's going to be rendered in the screen. I publish my map. And here I have a callback. Every time a registration loops over its iterative process, I can call a callback. This callback basically renders the correspondences in my visualization application that is over the network. And all I do here, this is the actual registration process for each individual scan that I provide as an input to the program. Let's just see how it looks like. So here I'm running, and this is the first iteration of the program. Here I draw as yellow data correspondences. The green is the source point cloud and the red is the target point cloud. What I did here is I first scanned my room in a certain position, then I moved a little bit to the front or forward, and then I scanned again. Of course, the two scans are misaligned, and I want to find what is the transformation that leads me from one point cloud to the other. And if I press enter, I perform the next step of the registration process. In the next step, I find new data associations. So here, these 3 points were associated with one single point in the cloud. Other data associations were also applied. If I step over again, you're going to see that almost every point now has acquired its correspondence because I've established there was a threshold beyond which they could not associate, but now they're close enough. Oh, now it becomes an association. If I do it over and over again, can you see that we were from a certain position and we're moving towards the actual position of the new scan. So that's the second position of my second sweep. I'm going to call the same algorithm, but I'm going to provide more scan as an input. Actually, I'm just going to call like this. So if I press enter, I'm trying to match the first scan to the second scan. The first one is the target, the second is the source. I press enter a few times. When they converge, now I load the third scan. And now I'm going to try to match the third scan against the target scan, the first one. So hopefully by the time, and of course the third scan is a new position, so I moved further to the direction of the curtains, which is right there. And I move to that direction and then perform a new scan. And here we can see that the algorithm allows me to, from the first position, what is the transformation that led me to the third position? And I can do it over and over again. This is now the fourth time. Fourth time was just a translation to the right side of the curtains. And the final one is a translation plus a rotation. So the final one will look like this. This is the trickiest and the hardest, one of the hardest things to match your scans. Rotations are extremely, if you don't do enough assumptions and if you don't have enough data or a good correspondence, you can easily deviate because the translations can converge to completely nonsensical positions and transformations just because it couldn't find associations as you iterate. But for this one, I've built a good enough algorithm, and I've also, it was a controlled scenario. It works just fine. So here you see the greens are converging, rotating towards the red to the point that, oh, they also, once more, they perfectly match. And ideally, we want the convergence point to be something like this. But sometimes you have errors in your measurement data, and sometimes you have noises and people walking and many different sources of noise. But it's possible for us to converge if we have good assumptions and good data associations and models. A small note about my renderer, this application here, is that I am right now running this application from within another dev container, and this other dev container is being displayed in my web browser. So there are a few dev container, let's say, plugins or extensions that you can very simply add to your dev container file that allows you to connect remotely desktop to your dev container and render openGL applications like this. If you want to know more, have a look at the Learning openGL repository that I'm going to share in the description, and in there you're going to see how this is done. But in the beginning of the video, I mentioned that it is also possible to perform mapping. How would that look like? It is very similar to the first step, but this time around, the two different scans are going to produce essentially different point clouds. They're going to produce point clouds that do not have all the correspondent points in each other. So they're going to have an overlapping region instead. They're not going to overlap everything. How does that look? Imagine I'm in the first position here and I performed my first LiDAR scan. Now I move to the second position and I perform a new scan. The problem now is how much of the first scan is overlapping with the second scan, such that I can actually trust that they can be merged. So what I'm trying to do is take the first scan, also try to match against the second scan like this. And if I apply some kind of heuristic or something smart, I can assume that, hey, what I've actually done is I've explored a new map, and then I can merge them. And I do this and notice that also out of that process comes a transformation that led me from the first position and the second position. The same T that we've talked before. So I hope you can see that just by performing two-dimensional LiDAR scans, you are almost fully capable of building a map as you scan new data, as you associate new data, and as you correlate previous scans as the new map. So the map starts to grow. And of course, if I do another LiDAR scan here, I can further enhance my map. And then I do another LiDAR scan here, and then I do another LiDAR scanner here. As long as I keep overlapping regions, as long as I have some overlap in between my scans, I can almost always assume that I am in the same space and I'm looking at the same thing, and I can correlate the data well enough that I can trust it that my map can grow. This is known as SLAM, Simultaneous Localization and Mapping. Thank you very much for watching. I hope you also find interest in this kind of things, how to use sensors to estimate the best position possible. And I find this very interesting, and maybe you can also share that interest with me. Once more, thank you for watching, and see you next time.